Hello, welcome to Introduction to Programming Using Java. This first chapter will give us a little bit of background of the Java programming language as well as hardware and software. Let's begin. So this chapter 1 is going to introduce us to computers and the internet. The book that we are using is Java How to Program Late Objects version. We'll talk more about objects in a bit. The objectives of this chapter, as we'll see in a bit, are learn about the exciting recent developments in the computer field utilizing Java. We'll see a little bit later in this chapter how Java is an extremely important language to learn when it comes to programming. Most companies will expect you to know the Java language, as well as it's a great language to begin with if you have not had any programming experience yet. We're going to learn about computer hardware and software and networking basics. This is fundamentally important if you to know about computers, whatever field you go into. If it deals with the computers, your employer is going to expect you to know the basics about computers, and chances are what we're going to deal with the hardware and software you probably know already. We're going to learn about the data hierarchy, how it relates to programming languages. We're going to learn about different types of programming languages. There are other programming languages besides Java that are out there. Some are very important languages as well. We're going to learn about the importance of Java and other programming languages. We're going to touch upon the concepts of object-oriented programming, that Java is an object-oriented programming language. We'll talk about that in a bit, how the past 15 years object-oriented languages were introduced, and it gives us the ability to program much larger types of programs. We're going to see the importance of the internet and the web. We're going to see the typical Java program development environment, how we were going to go and program in it. We're going to see an example of a Java application. We're going to see the recent software technologies, how they relate to Java. And then we're going to see how to keep up to date with information technologies. As I have already mentioned, Java is one of the world's very popular language for programming. We'll see why that is later on. Basically, one of the reasons is because you're able to use Java on different platforms, whether you have a smartphone or a laptop or you're programming for the internet. It's a very versatile language, as well as being able to run on many different machines. We'll see why that is in a bit. It's probably the world's most widely used computer programming language. I forgot the exact number on how many different. If you would see how many different programs are running in Java, I believe, according to the book anyway, it's over 2 billion PCs are running Java programs. We're going to learn how to write instructions, commands, how to write instructions, commanding computers to perform tasks. We're going to start off with something very basic, like a hello world program, where all the computer does is print the words hello world. The software that's necessary to write a program is the compiler we'll use is going to be Eclipse. I'll show you how to install that in a bit, and it's the software that will enable us to program. We're going to, like I said before, learn about object-oriented programming, and that's a very important programming methodology in order to write programs. We're going to create and work with many software objects. Objects are as you can see from object-oriented, it's one of the key features of an object-oriented programming language. As it says here, many organizations, the preferred language for meeting their enterprise programming needs is Java. Java is, as I said, one of the most important and languages to start off with. It's also widely used for implementing internet applications, so that's a big plus. Also, according to Oracle, one of the creators of Java, it's 97% of enterprise desktops, 89% of PCs, and here's the number for 3 billion are utilizing the Java language. Just like many other programming languages, Java has evolved, and we're up to Java SE7 or SE8, and that's what this book is being based on. Programs evolve because new features are obviously added. In addition, it has to keep up with the growing needs of the customers that go and the programmers that go and use it. It's the standard edition contains the capabilities needed to develop desktop and server applications. We'll have no problem going and creating those applications. Prior to Java 8, Java supported 3 programming procedural programming, object-oriented programming, and generic programming. So we'll be able to, hopefully by the end of the day, write a very small program that will utilize these and demonstrate how to make programs. First, let's spend a few minutes talking about hardware and software. Basically, hardware is the physical computer and the components of the computer. If you're looking at your laptop now or your monitor, that's considered hardware. It's the physical part of the computer. Inside the computer, there is hard drive. There are hard drives. There's a motherboard, power supply. All that falls under the category of hardware, as opposed to software. Software are it's the code that one writes and runs in the computer would be considered software. So obviously, we need both of those in order to run any type of program. And this exists also if you're dealing with your phone. If you're dealing with a smartphone, the hardware would be the phone itself, and the processes are inside, and the software would be the apps that are running on the phone. So computers can perform calculations and make logical decisions faster than human beings can, because they're inside. There's a CPU, a central processing unit, that takes the commands, and as we'll see also in a few slides, that the computers each year get faster and faster. And because of that, we have to often write code that can keep up with the processors. Often, for example, many years ago, 15, 20 years ago, the CPU was perhaps an 8-bit or 16-bit CPU, which means that there's between only 8 channels or 16 channels that are able to pass information to the central processing unit. Nowadays, we're up to 64, even 128 bits of information can be passed. So because more information can be passed, the central processing unit could process information faster and therefore run the programs faster. The software that's written has to keep up to date with the newest CPUs. Today's personal computers can perform billions of calculations in 1 second, obviously much more than humans can perform in a lifetime. It's able to process all this information. I mean, even me moving my mouse, as you see across the screen here, internally what's happening is that it's processing where my mouse is. Am I on a part of the screen that needs to make some type of change? If I highlight something, if I highlight this here, the inside of this PowerPoint presentation, it does those calculations as far as highlighting the information, and it's done within. There's a lot of things happening behind the scenes, but just moving my mouse across the screen, there are thousands of calculations that the processor has to done within a nanosecond of as it's happening. There are computers that are much more powerful than the desktop computer that we have. I'm not going to get into all the different types of laptops or processors that are around now. At the time of this recording, the newest processor is the Intel i9. There's an i7, i5, i3 with different versions. We're up to version 8. And it's fairly fast. This computer I'm running on right now is an i5 computer. It's an Intel i5, and it's quite fast. It's not the newest computer. The newest chips go down in price as time goes on. The newest, again, at the time of this recording, the i9 has been released, and it goes for about $2,000, depending on which variety you want to get, as opposed, and that i9 chip, the same way that i3 at one point was thousands of dollars, it's now you could pick an i3 chip up perhaps for $50, $60. So as time goes on, the chips get cheaper, but you still get the computing power. Getting back to supercomputers are used by large institutions. They'll be used by large corporations as well as the government. They're used to perform thousands of trillions of instructions per second. There are many reasons why they would go and use it. They're often for like weather forecasting or for financial reasons, or the military use it for different types of calculations. And you could look online for different pictures of how supercomputers look. Basically, it's a large box with many processors inside of it, and it's um, obviously we don't need it for performing our small programs, but they do exist. Computers process data under the control of sequences of instructions called computer programs. That's what this class is all about, how to go and program a program in Java, and that's what we will be going and creating. The software programs that will guide the computer through the ordered actions specified by the people are called computer programmers. That's what we are. We computer program, and we're going to hopefully learn a program methodology that's enhancing programming productivity, reducing software development costs, object-oriented programming. It's here's that word again, object-oriented programming. Basically, the larger the program, if you could break it down into its fundamental parts, that would be considered, that break it down into objects, you could reuse that object again and again, and thereby reuse your code. If you could reuse your code, it's going to save companies and your own self time in the development of the program that you're creating. If you would break a computer down into its parts, we have the computer consists of various devices referred to as hardware, as we said before. For example, the keyboard that you see in front of you is part of the hardware. Well, if you're on a phone, I guess it's a virtual keyboard, so that's maybe not as a hardware, but if you're on a laptop or desktop, you'll see a keyboard, a screen, a mouse, hard disk, memory, DVD drives, and processing units. Those are all fall under the hardware. If you could tap it with your finger, that's considered hardware. Computer costs are dropping dramatically owing to rapid development in hardware and software technologies. Pretty much computers just go down in price and become obsolete. The computer that you might spend $600, $700, $800 on today, if you would try to sell it in 3 or 4 years, the price will probably drop to $300 or $400. So, and that's okay. I mean, computer hardware changes all the time, but you want to get what currently is relatively fast and performs well. It doesn't mean you have to get if I were to purchase a laptop today, I would probably not go for the fastest one. I'll probably go for the 2 or 3 generations down from the newest technology. As it says over here, computers that might have filled large rooms and cost millions of dollars decades ago are now inscribed on silicon chips, smaller than a fingernail, consisting perhaps of a few dollars each, which is true. I don't want to, I mean, I've seen videos of we'll get to how to information being stored, but even storing information has gone down in price dramatically. What you could fit onto the amount of pictures that you could fit onto your phone or on a flash drive would not have even been possible 20, 30 years ago. Would take up rooms and rooms of space because the way that storage has decreased in size and in speed dramatically. So basically, things get smaller and cheaper as time goes on. The silicon chip technology has made computing so economical that computers have become a commodity. It's used by everybody, and and that's what makes programming them a very popular thing for programmers to learn. There's a concept in relation to this called Moore's Law. Every year or two, the capabilities of computers have approximately doubled inexpensively. In other words, technology has become cheaper and faster as time goes along. This remarkable trend often is called Moore's Law, named for the person who identified the trend. And Moore's Law and related observations applies especially to the amount of memory that computers have for programs, the amount of secondary storage, such as a disk, the storage device. And here's actually I brought in on another screen here. I use 2 different screens. I'm going to bring another screen on right now to show you. Hopefully you can see this. All right, this is an example of this picture over here of Moore's Law. We see that as time goes on, 1970 up to, they're predicting, you could actually make predictions up till later on what's going to happen, but we see that pretty much it's doubled every other year. And what we're about up to here, which makes sense, right? We mentioned before the i7, which is over here. And this gives us the ability to run computers faster and use the storage might not become less storage that you need, but the storage becomes cheaper. There is, they say, a finite amount of this eventually will level off. I mean, there is only so much you're able to store. I mean, when you get down to the molecular level, you get to you can only fit so much into amount of space, although at that point they might start using compression, but it's an interesting law to go and follow. Similar growth has occurred in communications field as well. When you talk about communications, you might be talking about cell phones, or you might be talking about, let's say telephone, but nowadays it's not even common for people not to even have telephones. They might just have a cell phone in their house. Costs have plummeted. There's enormous demand for communication bandwidth. Bandwidth is the amount of information that's being able to carry through wires as well as online. And such phenomenal improvement is fostering the information revolution. So that's the times that we're living in. Its information is being able to pass so fast and so much each day. And there's quadrillions of bits of data that's being stored every single day. Computers come in a variety of sizes. It might be a large computer, like we said before, like a supercomputer, or it could be your cell phone, which is obviously much smaller. So regardless of the different physical appearances of the computer, computers can be envisioned as divided into various logical units or sections. That's what these next slides deal with. So the first one, I'm not sure if you can read this, but there's a copy of this in your book, is the input unit. And this is the receiving part of a computer. And there are a lot of different ways that we're able to get input into a computer. Might be the most common way is through a keyboard. As I mentioned on a laptop, it might be the actual keyboard that you tap the keys. On your smartphone, it might be the virtual keyboard. We're able to go and input information. But there are other ways as well that you're able to get information. You could get information nowadays through voice commands, where you actually go and speak. Obviously, it's software that's going to interpret your information, your speech, into some type of code, but that still is a form of input. Another form of input might be actual data. If you're processing a file, that file that you're processing is also input. When I process grades, I take all the grades that I have inputted the grades at one point, and then once those grades have been inputted, I'll input them again into another program to have the program go and actually produce some type of grade. So that's the input part of a computer. Then we have, of course, the output unit, and output also has a few different forms. You might have, well, the most common would be the screen that you're seeing is a form of output based on the input, and this input can even be my mouse moving around the screen, or this PowerPoint presentation might be a form of input. The actual input would be this PowerPoint presentation itself, which you could also download online. And the output would be the result of what we're going and what we're seeing. The internet's a good example of output. That's a commonly used device. DVDs are, or CDs and videos are another form of output. Then there's something called the memory unit. And the memory is what stores your information in short-term memory. When I say short-term, that it's inside of the computer, there is a part called memory. And anything that you see on the screen has to go through memory in order to be processed or shown on the screen. I like to make the analogy to a mind that's going and a person has, if I ask someone to, I don't know, quote statistics from a specific year, they won't know them off the top of their head. They'll have to go and look them up in some type of encyclopedia or online or whatever. And then when they tell me that information, it's currently inside of their memory unit, their mind, and they're able to tell me that information. A few days later, I might ask information, again, the same information, they might not remember it. So the same thing in a computer. In order for something to be remembered or be actually produced, it has to go through the memory unit, and that's short term. When the computer is turned off, that memory is lost, and we have to go and retrieve that information. Fortunately, nowadays, as we saw on previous slides, memory gets cheaper and larger as time goes on. So nowadays we're able to store gigabytes of information. It's not uncommon to buy, when you get a laptop now, you get it with 4 gigabytes of memory, 8 gigabytes, 16, and the more memory you have, the faster recall the computer will actually have. We have the central processing unit, which is usually referred to as a CPU. And this is the part of the computer or your phone or whatever that's actually able to process that information. The CPU is broken down into a few different components. And again, for programming, it's not so very important to know this, but as a programmer, you should be aware that there is a CPU inside of your computer. There are, as I said, there are a few parts of it. There's the ALU, which is the arithmetic and logic unit, which is actually taking and processing the information. You have the actual processing unit itself that's going to go and process that information. And as anything else with computers, the CPUs have become cheaper with time and more powerful. And every single computer that you would use will have some type of CPU inside of it. Then there's the secondary storage unit. The secondary storage unit can be equated, like I said before, to a library, whereas memory is once you consume the information, it's currently available. But if you want to go back and get the other information, you have to go to that secondary storage unit. That could be, it's referred to as perhaps a hard disk, could be the permanent storage, and that hard disk is maintained once the computer is turned off. Might be a USB drive. When you store pictures or music to a USB drive, when you plug it in again, the information is there. That's considered a secondary storage device. But again, that information has to go through memory to actually work somewhere. So you might have secondary storage is much cheaper than memory. It's also much slower. So if you have a large image that you're doing video editing on, that image itself might be, I don't know, might be 40, 50, 60 gigabytes large, and that is loaded into the memory, so you could actually go and make changes. And once your changes are made, you want to make sure to change it back in the actual, save it to your secondary storage to make sure that you have it for next time. Data is stored inside of this of the hard drive, or it could be the memory as well, in small items. There's a data hierarchy of information. This says data items processed by computers in the form of data hierarchy that becomes larger and more complex in structure. The smallest item, the smallest thing that a computer could store is a bit, 1 bit of information. Now, when I say a bit, usually we refer to them a bit in the computers as a 1 or a 0, but obviously if you would open up a computer, search as you may, you will never see an actual 0 or a 1, right? Because nothing is writing information like that, a 1 and a 0. Usually we refer to it as 1 and 0, and that internally inside of a computer would probably refer to as a magnetized part of the hard drive or memory that is either polarized or non-polarized. Or in the terms, if you're, let's say, a DVD, it might be a very, very small, meaning if you get the very, very powerful microscope, you might be able to see a small section that has a laser etched in or not etched. So that's either a 0 or a 1, or we also might refer to it as an on or an off. Incidentally, if you worldwide, it's known as a 1 and a 0. That's why whatever electronic component you might see, they often have the on switch is considered a 1 and a 0 is considered off. So that's worldwide. So that's why 1 is considered on and a 0 is considered off. So if we have enough bits together, 8 bits as we see down here, and again, the book will go into this more, and as necessary, I'll make sure to point it out as we come across it in the actual programming, once you get to a little more programming here as opposed to theory. that you have 8 bits, which is either a 0 or a 1, and 8 bits together is called a byte. And once we get into bytes, we're able to actually start doing some information, start able to record stuff. There is a once you have 8 bits, actually 16 bits, where you probably need, we're able to get letters. How so? Well, there's another universal way of storing information is once you get a bunch of bits together, they break down into what's called a Unicode or ASCII code. And that ASCII code will be able to, once you have these bits together, the combination of zeros and ones might turn into, if you look at the ASCII chart, you're able to see that a certain combination might turn into an S or a B. Now these are considered, it's not, or it might be the character 1 or 8. Now that's not the number 1 or 8, it's the character equivalent of a 1 or an 8. And enough of these ASCII codes together are going to give you what's called files. And these files that are put together might be, here in this example, they just have some names here, but it could be a file that we program in Java, an actual file that we're going to create. Enough files, we're able to go and make what's called a record. Getting back to the concept of bits, under this data hierarchy, the smallest data item in a computer is, I said, a 0 or a 1. We refer to it as 0 or a 1. It's not, you don't actually see that inside the computer, but we refer to it as 0 or 1. This is called a bit, short for the binary digit. And they say here that it's remarkably the impressive functions performed by the computer involves only the simplest manipulations of zeros and ones. Obviously, you have to stack them together put them together to do these type of manipulations, but everything in computer just breaks down to a 0 or a 1. And a 0 or 1 is under the family of a binary, right? When we count to 10, we're using a decimal, we're using 10 digits. That's what our numbering system is based on. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 there, so it's a decimal system. Binary is just 2. In computers, we'll see a little bit later on, 8 is a common one. It's 0 through 7 makes 8. It's octal. And sometimes we deal with 16. We do 0 through 9, and then A through F to continue on. And that's 16, which is called hexadecimal. So, but we're dealing in computers, we'll just deal with, it's a binary system. It's just a 0 and a 1. So with characters, as we see here, we prefer to work with decimal digits, 0 through 9, uppercase letters, A through Z, lowercase letters, lowercase a through Z, and special symbols, whatever these symbols are, a question mark and an ampersand and a dollar sign and so on. So digits, letters, and special symbols are known as characters. When you look down at your keyboard, you see a bunch of characters. The computer character set is a set of all characters used to write programs that represent data item on the devices. That's how the computer is able to store information and how we're able to actually go and program. The computer processes only ones and zeros, so every character is represented as a pattern of zeros and ones. So this actual pattern is used in the form of what's called Unicode, and they're characters that are composed of 1s, 2s, or 4 bytes. And we said before that a byte is 8 bits, so it's either going to be 1 byte, which is 8 bits, 2 bytes, which is 16 bits, or 4, which is going to be 32 bits. We'll be able to go and see which character is represented by these bits of information. The Unicode contains characters for many of the world's languages. It started off with just ASCII, and I know the term ASCII is referred to as the very first. It's way of a chart of being able to do A through Z, uppercase, lowercase, and a few other ones. But quickly we saw that wasn't enough for other letters, other word letters that are alphabets that are being used. So they went and created this Unicode chart, and it's used worldwide. So the Unicode chart that we have, and there's, if you're looking back in the book at the chart for this ASCII chart or for the Unicode chart, It contains all the letters. It's used worldwide, so you don't have to worry about programming on your computer for another country because this Unicode chart is used all over the world. If you put enough of these characters together, you will get a file. A file is a group of related records. As we said before, records are a bunch of characters that have been put to fields, and then files that are put together. So more generally, a file contains arbitrary data in arbitrary format. We're able to go and to store these files on the computer and use them for whatever purposes they're dedicated for. In some operating systems, a file is viewed simply as a sequence of bytes, because really that's all they are, is just a bunch of zeros and ones that are put together and organized. Any organization of the bytes in a file, such as organizing data into records, is a view created by the application programmer. Depending on how we read the information, that's how we're going to go and deal with it. So if we get enough files together, you could create what's called a database. And then, though this is not a database course, you could take a database course, and a database is a collection of data that's organized for easy access and manipulation. Databasing is very important for a programmer, although we're not going to deal with it a whole lot inside of this Java programming class. It is how most computer organizations run. They run off of what's called a database. For example, when a student takes a course, the course that they're taking is stored inside of a database. More than that, all the students are in a database, and the courses that the students are taking, along with the student's name, they're related to each other. So it's what's called a relational database. The most popular databases model is a relational database in which data is stored in what's called simple tables. A table includes records and fields, and using those together, it's a quite powerful way of going and storing information. It makes it easy to search and to sort this information. Otherwise, it'd be quite difficult to go and to sort that information. Data could get quite large. This section is called big data. The amount of data being produced worldwide is enormous and growing very, very, very fast. According to IBM, which is a leader in databasing and programming, there are approximately 2.5 quadrillion bytes, which is a huge amount. I can't even imagine how much of information that is. It's stored daily. So not just weekly or monthly or yearly, it's stored daily. And this type, if you could think about all the, I don't know, videos that are stored up on the computer, and I don't know, news broadcasts and newspapers, all this information is now stored nowadays. It's not like, I guess, in the olden times, and things are just even printing in the olden days, you used to just get a lot of print, but now that information is stored digitally, and we're able to get that information back. Here's a link if you want to see that. So the big data applications deals with such massive amounts of big data, and this field is growing quickly, creating lots of opportunity for software developers to go into data mine this information and to take a look at it and to search it and get information from it. So this here is a breakdown of the size abilities. We deal with, I said before, that there's a bit, and you have first the bit, then your next level up, you have the kilobyte, megabyte, gigabyte, terabyte, and each of these is 1,000 more of the previous one. You can see how it's growing here by 3 zeros each. So 1 gigabyte contains 1,000 megabytes, which contains 1,000 kilobytes. And then you have a terabyte, which is probably what your computer is in terms of terabytes. And we see how many zeros there are to a terabyte. And it goes on from there. They've not gotten to the point where we have storages into these numbers here, but perhaps one day they will. When a programmer actually makes a program, they have to make sure that the machine, the computer that they're using, understands the language that the actual program that's being run. So, as it says here, programmers write instructions in various programming languages, some directly understandable by computers and other required intermediate translation steps. So these are divided into three different types. One is called a machine language, one's called an assembly language, and one's called a higher level language. What we deal with in Java, as we'll see, is a higher level language. A machine language is very cryptic. It's a way of it's very easy for a machine to process machine language because it's written in the native language that the CPU will understand. And these higher level languages, once you read language, the processor will not the processor, the program itself, whether it be the Java program or the C++ program, the actual program, the compiler will be able to convert that language into the machine language that the computer will then understand and carry out the tasks. These next slides will introduce us to each of them. Again, for the programming, it's not for programming Java, this is good to know, but you don't have to be so concerned with the different languages that are or how the process is for converting them. I mean, if you want to get into like faster code, you should know more about machine language, but it's just good to know as a programmer. So first we have machine language, and any computer can directly understand only its own machine language defined by its hardware design, which means pretty much that if you're dealing with a phone, if you're dealing with a mobile device, even the types of mobile devices are different, it will, that specific machine, that's the phone versus a computer, that's two different languages that the two of them know. The basic language that a machine knows is all dependent on the device, the CPU, that's the architecture that's running the machine. That's why there are people who use a Mac computer versus a PC. It's different operating system. It's a different way that the machine's going to understand the language. Also with a phone, the phone is different than a computer. If you write your program for on your laptop or your PC and try to run it on a phone, it won't run unless you put it through a few different. You convert it to a machine language that the phone will actually go and understand. So that's machine dependent. A particular machine language can be used on only one type of computer. Then we have assembly languages and assemblers. It's in English, so machine language is just a bunch of non-codable, not readable. It's a bunch of basic cryptic ways that the machine understands it. Then we have assembly language, and that's in English-like abbreviations that represent elementary operations. It's called assembly language. It actually is a language called assembly language, and if you have a chance, it's worthwhile to look up a few videos on it. It's also cryptic. For example, if you want to move one bit of information from one part of the program to another, it's like an MOV command, which stands for move. And so it all depends on the type of what you want to do. And there's something called registers that you only have a specific amount of memory for these assembly languages. And there's a translated program called assemblers that converts the early assembly language into programs into the machine language. So everything comes back down to the machine language. So if you were to program in assembly language, assembly language, it would be converted the next step into the machine language. Then we get to what we're learning, which is higher level languages and compilers. So a higher level language, it's a single statement accomplished through different tasks, and it works through what's called a compiler, and it converts a high-level language program into machine language. So you don't have to worry about the actual machine language or the assembly language. It will do it for you automatically. It allows you to write instructions that look almost like everyday English and contain commonly used mathematical notations. And here's an example. This is almost a valid bit of code that you might see in Java. It's missing a few things like a semicolon, and you have to initiate these words, but you might have gross pay, which might be a part of memory that's taking the information is equal to base pay, so whatever base pay is, plus overtime pay. So these two will be added together, and they will be stored into this gross pay, what we'll see later on to be a variable. So this is what we're learning as a higher level languages. You don't have to worry about the machine language. We don't have to worry about it. It was I took an assembly course once, and it was just very tedious, especially knowing that there are higher level languages out there. What it did teach me was it teaches you a little bit to appreciate data storage and how to speed your programs up, because if you write something in assembly language, you really have to know the nuances and the way that the processor stores information in order to make your program work fast and efficient. Interpreter is a compiling a higher level language program into machine language, and it can take considerable computer time. Again, when we say considerable time nowadays, that's might be talking seconds for it to convert it. But hopefully, by the end of these files, we'll see a small program where just even printing something on the screen, we'll write a small program. It will convert it and it will print the information onto the screen. Interpreter programs developer to execute higher level language programs directly and avoiding the delay or compilation, although they run slower than compiled programs. Compiled programs are programs that have already been compiled once. They've been converted from these higher level languages into the assembly language, into the machine language, and they're able to run faster. If you take a look at your Windows or Mac, whatever platform you're on, you could take a look at the extensions of your programs, and anything that ends with an exe, it's called an executable, that has already been converted into a executable program that the computer could run immediately. It's already been converted into machine type language. We're able to go and run it, as opposed to a program that ends, let's say, in a Java extension, where it's going to have to go through a process of being converted in order to go and to run that program. Because Java is an object-oriented language, it's worthwhile to spend a few minutes talking about the concept of an object. An object, or more precisely, the classes object, come from the essential reusable software components. There are data objects, time objects, audio objects, video objects, and so on. You can make anything into an object, and almost any noun can be reasonably represented as a software object in terms of the attributes that exists. For example, as long as you can give it a name, a color, and a size, and behaviors such as if you're able to calculate it or move it, we're able to create it, make something into an object. Software, let me go back there. Software developers groups can use a modular object-oriented design and implementation approach to be much more productive than with earlier popular techniques, what's called structural programming. Object-oriented programming is much easier to understand and to use. Basically, what that means is, instead of writing bits of code again and again and again, you might turn that bit of code into what's called an object, and they're going to have an example in a moment. And you could reuse that object and give that object new parts, and once you have those different components, you're able to utilize them in a program. So they're using this example as an automobile as an object. The automobile, like a car, is an object. So it's going to start with a simple analogy. Suppose you want to drive a car and make it go faster by pressing its accelerator pedal. Before you can drive a car, someone has to design it. So a car typically begins as an engineering drawing, similar to the blueprints of a house. The drawing includes design for a accelerator pedal, to make it go faster and slower. The pedal hides from the driver the complex mechanisms that actually make the car go faster. If you think about it, they don't really care. We just care about the actual pedal itself. We don't care what happens internally, as long as the car goes faster. So just as the brake pedal hides the mechanisms that slow the car, and the steering wheel hides the mechanism that turn the car, they exist, and they have to be programmed within the car itself. So this enables people with little or no knowledge of how engines work, or how the braking works or steering works, to drive the car easily. We don't really care how it works, as long as it does work. So before you can drive a car, it must be built from the engineering drawings that describe it. A complete car has an actual accelerator pedal to make it go faster, but even that's not enough. The car won't accelerate on its own. So the driver must press the pedal in order to accelerate the car. Again, we don't care how it works as long as it goes and it works. So the methods of a class perform a task in a program require a method. The method houses the program statements that actually perform the task itself. These hides the statements from the user, just as accelerator pedal is hidden from the car, the driver mechanism of making the car go faster. In Java, we create program units called classes to hold the set of methods that perform the class's task, as we'll see when we create our first program. A class is similar in concept to a car's engineering drawings, in which house the design of accelerator pedal and steering wheel and so on. So then there's this concept of instantiation. Just as someone has to build a car from its engineering drawings before you can actually drive the car, you must build an object. You must build the concept itself of a class before the program can be performed. The tasks that the car's methods is defined, an object is then referred to as an instance of its class. So you first make the concept of it, then you instantiate it. Basically reuse is once you create it, you could reuse it again and again. So just as a car's engineering drawings can be reused many times to build many cars, you can reuse your class many times to build many more objects. The reuse of existing classes when building new classes and per programming saves time and effort, because once you make it once, you don't have to make it, you don't have to do it again. Reusing it also helps to build more reliable and effective systems. The same way that let's say that there's a mistake in your code, if you just go back and change the initial class itself, it will trickle down to the reuse, so all the reuses of it will be fixed as well. So when you drive a car, pressing its pedal sends a message to the car. So those are messages and method calls. So we're able to send messages to the classes that we go and create. When we perform these classes, it's called a method, right? Performing a task in a program requires what's called a method. This is the method. It houses the program statements that actually perform the task. A lot of this will be a little clearer when we make our first program, where these methods hide the statements from the user, just as accelerator, pedal, the car hides the driver from the mechanism of the car itself. In Java, we create programs called classes to house that information. Oh, I mentioned that already. Hold on a second. Sorry about that. My computer had to reboot. We have, we just spoke about, backtrack for a second, the messages and method calls. We have the attributes and instance variables. The same way that a car might have an attribute, its color, its number of doors, anything about a car, so too programs as well have attributes. And if you make a class properly, you're able to create it that we could change those attributes. So the car's attributes are represented as part of the design in its engineering diagrams. Every car, sorry about that. So it has the color, it has the amount of miles it might get, and so on. So every car maintains its own attributes. So too, in a program, it's going to have its own, the different methods are going to have their own attributes. Each car knows how much gas is in its own gas tank, but not how much is in the tanks of other cars. And that's an important concept in programming as well, because if we create an object, then we know the object knows its information about itself, but it doesn't know the information about other objects. An object has attributes that it carries along as it's used in a program. It's specified as part of the object's class. For example, a bank account object has a balance attribute that represents the amount of money in the account. Each bank account object knows the balance of its account it represents, but not the balance of other ones. So that's an important feature inside of programming, which comes down to what's called encapsulation. The classes and their objects are encapsulated. They're encased within their own. It only has information about itself. Objects may communicate with other objects, but they're normally not allowed to know how other objects are implemented. That's the concept behind encapsulation. It's also known as information hiding. As we'll see, it's crucial to good software engineering in order to create a program that's the information is encapsulated, and that way one part of the program can't interfere with other parts of the program. Another key feature of programming is called inheritance. The concept of inheritance is that a new class of object can be created conveniently by inheritance, which is the new class starts with the characteristics of an existing class, which is called, as we'll see, a superclass, and you're able to customize it by a bit of information by passing it perhaps its color or its size, or in a programming way like how much data is necessary for that specific class. In our car analogy, it might be a class called convertible. It certainly is an object of the more general class automobile, but more specifically, the roof can be raised or lowered. So that's the concept of inheritance. I'm going to stop this recording here so I could post it, and I will try to get the other one out later today or tomorrow. I have posted some homework assignments based off of the textbook that you could get off of the Moodle site. If you have questions, please let me know. If you have comments, please let me know. You can email me with any questions or information you might have. Thank you for watching.